Chapter 4, Part 3, Naming Cyclic Alkanes, also known as cycloalkanes. So, how to? First, count the number of carbons to get the parent name. Add the prefix cyclo. If you only have one substituent on a cycloalkane, it does not need a number because that carbon would automatically be number 1. If you have 2 or more substituents, the rules get a little more complicated. So if you have 2 substituents, you number starting with the first alphabetically, and in the direction, counterclockwise or clockwise, that gives the next substituent the lowest possible number. If you have 3 or more substituents, you number in the way that gives the lowest set of numbers possible. Now, the only difference for these is if you have a high-ranking substitution, like a hydroxyl group. If you have a single ring attached to a carbon chain that is longer than the number of carbons in the ring, or if the carbon chain has a functional group on it, the ring becomes a substituent on the carbon chain. If you have more than one ring attached to a single chain, the rings become substituents. So again, this is one of the situations where this is a lot of rules and they don't make a lot of sense until you see them in practice. So let's practice. Go ahead and try your hand at the first row. So pause and work on them yourself. Okay, so the first one is pretty simple. There are 6 total carbons in this structure. So this is a hexane. More specifically, it is cyclohexane. Now, if we take the same structure and we add on a substitution, such as an isopropyl group, it becomes isopropyl cyclohexane. Or you could call it 1-methyl-ethyl cyclohexane. The next one, we have 1, 2, 3, 4, 5 carbons. So this is cyclopentane. And we have a bromo substituent. Notice that I gave it the number 1 because the substituent always has to have the lowest number. And if there's only one substituent, it's number 1. So we call this bromo cyclopentane. Now go ahead and pause and try the next row. Okay, so looking at the first example, we have a hydroxyl group and an ethyl group. Now ethyl comes first alphabetically, but the hydroxyl group has a higher priority than ethyl. And the reason why is just that alcohols are reactive. And so that's going to indicate how the molecule behaves. So we're going to give it precedence. And that's also why it ends up having an effect on the suffix of the name, is so that you can be sure that you know that, okay, this molecule is going to act like an alcohol. So we're going to give the hydroxyl carbon the number 1 position. And we're going to number clockwise because that gives the ethyl group the number 3. If we were to number counterclockwise, it would give it the number 5. And we want the overall lowest numbering scheme possible. So this is 3-ethyl cyclohexanol. Now, anytime that you come up with a name, especially as we start to add more and more pieces, just go back and look at your name and make sure that you've included all the describing factors. A good way to do this is to take your name and draw it without looking at the original structure. Draw what your name says. So, for example, maybe you forgot to include cyclo. So you would have 3-ethyl hexanol. You'd have to draw out 6 carbons. You don't really know where the alcohol is because no number was there, but you know that the 3rd carbon has an ethyl group. So already you know that this is not right. And that would remind you like, oh, okay, I need to add in the cyclo. Now the next one, we have an ethyl and a methyl group. So neither of them is really more important than the other. So we're going to do this alphabetically. E comes before M. So the ethyl group is carbon number 1. And we're going to number counterclockwise because that brings us to the methyl group sooner. So the name of this molecule would be 1-ethyl 3-methyl-cycloheptane. So our next molecule has 3 substituents. So at this point, what you want to do is pick the numbering scheme that's going to give you the lowest overall numbers. I'm going to show you an example by providing you 3 different numbering schemes, although we could do many more. So the correct numbering scheme is to start at the methyl group and go to the ethyl, 3, 4. So I'm going to cut out the 3 there and just give you 4. So this first numbering scheme would be 1, 2, 4. We could also number starting at the ethyl group, and let's say that we go clockwise as well. That'd be 1, 2, 3, 4, 5, 6. That numbering scheme would be 1, 3, 6. We could also start at the chloro group and go counterclockwise. That would give us 1, 3, 4. So it's pretty clear looking at these which one is the correct one. And we could have come up with other ones by alternating, clockwise and counterclockwise. But if we use the orange numbering scheme, we'll get to the correct name. So the next step is to alphabetize your substituent names. You have an ethyl group, a chloro group, and a methyl group. And I did just say those in alphabetical order already. So 2 ethyl, 4 chloro, 1 methyl, cyclohexane. Now, our last thing here in just naming straightforward cycloalkanes is what about when the cycloalkane is a substituent? So for example, this is a cyclobutane, but it's on a chain that is longer. There are 5 carbons in this chain, so that makes it the more important thing. So we would call this 1-cyclobutyl pentane. On the next one, the carbon chain is not the longest thing here, but we have 2 cyclohexyl groups. And because there are 2 of them, it makes it really difficult to say, like, how would I name this as a substituent on this ring, right? Whatever you came up with, it would be convoluted, or at least more convoluted than just saying 1,3-dicyclohexyl propane, which is the name. So the IUPAC structure of the naming always tries to give the most straightforward, unambiguous name possible. So speaking of unambiguous names and trying to be straightforward, there are molecules that are called bicyclic alkanes, and generally their structures are kind of complex and the naming is a little complex, but once you have it down, it's pretty easy to do. So if you have 2 fused or bridged rings, they're called bicycloalkanes. So the bicyclo is indicating that you have 2 cyclic structures, just like a bicycle indicates that you have 2 wheels. Use the total number of carbon atoms in the rings as the parent name. So for example, in this structure, we have 6 carbon atoms in one ring. And we also kind of have, you could look at this as 2 5-membered rings fused together, or bridged together, really. And the way that you would draw this in a skeletal form is like this. So you can see, you can look at this as a 6-membered ring with a 1-carbon bridge between opposite carbons. And you can also look at it from the side. So imagine that your eyeballs are looking at this from this angle. Here is your cyclohexane ring. And then you'd have that bridge sticking up away from the cyclohexane ring. So this carbon is this carbon. So this molecule is a bicycloheptane because there are 7 carbons total. Now, the naming for this is based on the number of carbons in the bridges. And the bridges are the carbon atoms that connect your bridge heads. So the bridge heads are the carbons that are attached to many carbons, holding all the pieces of this molecule together. And the bridges are the ones in between. So we already know that the main part of this name is a bicycloheptane. So the next step is to add in brackets the number of carbons in each bridge in decreasing order. So we had two 2-carbon bridges and one 1-carbon bridge. So the name of this compound is bicyclo-2,2,1-heptane. This has a common name of norbornane. Now you can also have molecules that are fused together. And this one's really interesting because since it's fused, one of your bridges has no carbons in it. So we have our 2 bridge heads, a 1-carbon bridge, a 1-carbon bridge, and a 0-carbon bridge. So this is bicyclo-1,1,0-butane because there are 4 carbons total. And this is what it means to be fused. So you can kind of picture this as 2 cyclopropanes that have been fused together here. Although you only end up with 4 total carbons. When you have substituents present, you number starting at one bridgehead in the direction of the longest bridge, towards the next bridgehead, then along the next longest, and the shortest bridge is numbered last. So that sounds really confusing. Let's take a look at a picture here. It's kind of like creating a spiral. So in this molecule, we have 8 total carbons, and we also have the methyl group. So we start at one bridgehead, and this way we have a 2-carbon bridge. This way we have a 3-carbon bridge. So we're going to go in the direction of the 3-carbon bridge. And then when you get to the next bridgehead, you want to pick your next longest bridge. So we're comparing 2-carbon bridge versus the 1-carbon bridge. We're going to follow the 2-carbon bridge. Now you're back at your first bridgehead, carbon number 1. You have to count the last bridge, and that's how you give the numbering scheme for a bicyclic alkane. So this is 8-methyl bicyclo 3,2,1-octane. Now we can also look at an example for a fused molecule. So you start at a bridgehead, and you have the choice of going down a 3-carbon bridge or a 4-carbon bridge. So we're going to pick the 4-carbon bridge, and that brings us all the way around to our next bridgehead, where we have to choose either the 3-carbon bridge or the 0-carbon bridge. So we pick the 3-carbon bridge. And then when we get to our original bridgehead, we have to count the 0-carbon bridge. So this is 8-methyl bicyclo 4,3,0-nonane. Is there 9 total carbons within the bicyclic structure?